In this tutorial, we use ScopeSim to simulate MICADO spectroscopy, starting with a single detector before moving on to the full detector array. We begin with our standard Python packages, NumPy and Matplotlib for handling and visualizing the data, AstroPy for units and fits files, and of course ScopeSim together with the templates. We will simulate a single star, so we import this directly. I also prepare a small plotting function, mainly for visualizing the later 3x3 detector mosaic, although it works just as well for a single detector image. Feel free to skip this part entirely and use your own plotting routines if you prefer. Now let's define our source. We will simulate a K5 giant star with a J-band brightness of 9 magnitudes. For clarity and convenience, we define the observing configuration explicitly: the adaptive optics mode, the slit geometry, and the spectroscopy filters. Keeping these parameters separate, we can just switch between the different setups later without modifying the core code. Then we initialize the MICADO simulation with the selected modes. We also set the spectroscopy filters, define the detector window size, and choose the exposure setup. To keep things simple, we'll simulate a single exposure with an integration time of 1 hour. Now we can run the simulation on our source. As you can see, this actually takes quite a while. Even a single detector simulation can easily take several minutes. So before moving on to the full detector array, let's look at a simple way to speed things up during testing. By default, the spectral bin-width is about 0.02 nanometers. Let's increase this spectral bin-width by a factor 10. This reduces the spectral resolution, so we won't accurately reproduce narrow spectral features, but it is perfectly fine for testing configurations and inspecting the detector layout. And now the runtime is already much shorter. This is a very useful trick when testing configurations or experimenting with different observing modes, and we will keep this bin width for the rest of the tutorial. A very straightforward approach to look at the full detector would be to simply increase the detector window size. This allows us to capture a larger field on the detector and to get a quick look at where the spectrum falls. However, this still does not represent the full MICADO detector layout. It only enlarges the simulated detector region. To actually simulate the complete detector array, we need to access the optical train. So we retrieve the optical train and inspect its effects. Here you can see that the full detector array is disabled, while the detector window is enabled. For the full detector simulation, we simply reverse these settings. We enable the full detector array and disable the detector window. This enables the full 3x3 MICADO detector mosaic, with each detector having a size of 4096 pixels. We can now run the simulation again. Since this simulation can be quite computationally expensive still, it's a good idea to save the result as a fits file. That way, we don't need to rerun the full simulation every time we want to inspect or replot the data. And finally, let's visualize the detector array. The detectors are stored as separate fits extensions, so we first define the detector ordering corresponding to the physical detector layout. We can then loop over all detector extensions and use the plotting function from earlier to display each detector image in its correct position. And there we go. From here, you can continue with further analysis or processing, but for scientifically reliable results, remember to switch back to the original spectral bin width